Good morning, everybody. Going to give people a couple minutes to join in and then we'll start. Ooh, look at all these faces. Chat. And participants. All right, look at all these faces. 32, 33 people. Hey, Robert. Ooh, enjoying class from the outdoors.
The great outdoors.
Woohoo! So while people are doing this, I'm going to share my screen. Share. Okay, so while people are joining, I want to do a quick little recap of scalar product, and then I want to try and do a couple clicker questions by putting you into separate rooms, see how that works. So just real quick, started looking at the definition of the dot product, which is also known as the scalar product. And for two vectors, A and B, the dot product is defined as the magnitude of each vector multiplied together times the cosine of the angle between the two vectors.
Hey, Chad, the screen is like super small.
My screen?
Yeah, it's like just like a big old image of your face and like a tiny.
Let me stop this share for a second. Let me try and share the screen again. Is that working any better?
Yeah.
Okay, so dot product is defined as, let me see, more chat. Let's see what this says. Make it full screen. Okay, so hopefully it's full screen now. And let me go back to annotate, draw. Okay, so dot product, way it's defined is the magnitude of each vector times the cosine of the angle between it. The other way that you can get the dot product, if you are given x and y components of each vector, is I multiply the x components together plus the y components multiplied together plus the z components multiplied together. So those are our two ways of getting the dot product. And again, the reason we're caring about this, just so you know, is we're going to define work as the dot product of the force times the displacement. This is a little preview. So let me, I want to go to this mouse. And let me do this for a second. Okay, can everybody see? Let me erase this. Undo. Clear all drawings. Okay, can everybody see these clicker questions?
Yes.
Okay, so what I want to do is try something out. So, breakout rooms. Ooh, 42 people into. All right, so I'm going to try something I want to try creating breakout rooms. So I'm creating 9 breakout rooms with 4 to 5 participants each. And there's 2 clicker questions that I'd like to give you a minute or 2 to talk about together. So the first one, and let me annotate this again, draw. So the first one, question 9.1. There we go. So first question is, if the dot product of 2 non-zero vectors is 0, the vectors must be perpendicular to each other, true or false? The value of the dot product of 2 vectors depends upon the particular coordinate system being used, true or false? And the second one is 9.2. It says the scalar product of vector A, which is 3i plus 2j, and vector B is 10. So again, there's no units here. It's kind of generic, but you're given the dot product between vector A and B is 10. Vector A has a value of 3i plus 2j. The question is, which of the following vectors could be vector B? So what I'm going to try, I haven't done this before. I'm going to create some breakout rooms. You will all be separated into a breakout room with 4 or 5 other people. And I want to just give you a minute to discuss these 2 clicker questions. And I don't know if once I do a breakout room, whether you'll still be able to see it. So this is a little test. Doesn't this class have like 68? So this class has like 70 students, but situations are different. I don't expect every student to be able to come to every lecture live that they will be posting. All right, I'm creating rooms now. So open all rooms. So you should all be able to join a breakout room. So I'm not quite sure how this works on your end, but you should be able to join a room. I'm going to give you guys maybe a minute or 2 to discuss these 2 clicker questions, and then we'll go through them together. And I'm not even sure if you can still see me while you're doing these breakout rooms. So give it a try. And then, yeah, we'll reconvene in 1 minute. Oh, hello. Laura, do you have a question?
Hello?
Hello?
Are we in the breakout room?
I think we are.
We can't see the questions.
You can't see the questions?
No.
Okay, let me leave this breakout room and let me end, return to main session and breakout rooms. Let me close all rooms. All breakout rooms will close in 60 seconds. All right, so people hopefully are leaving the breakout rooms. I heard that when we do the breakout rooms, you can no longer see the screen.
It's just a room with the participants.
Okay, so you just see a room with participants. You can't actually see the clicker questions?
Yeah, you can't see the questions.
All right, good to know. So that's not gonna work. But you never know until you try. Let me just wait for everybody to get back here. Breakout rooms should be closed.
Joe?
Yep.
Hi. Were we supposed to watch the video before we come to the lecture?
The video from the last lecture?
I don't know. I think you sent us a bunch of links to the videos, but...
Oh, I just sent you links to the last, so the lecture that I gave yesterday and the office hours, I posted those along with the videos for lab 7.
Okay, so is it okay that I have no idea about this dot product and scalar product?
No, that's not okay. No. I have done a couple lectures on the dot product or scalar product. So yeah, ideally you are keeping up with the material. If you haven't gotten a chance to watch that yet, then yeah, watch it as soon as you can.
Okay, thank you.
So let me just share this screen again and we'll do the clicker questions together. So let me annotate, clear all drawings. Clear all drawings.
Is that vector, is that for the 2, is that 10i or what?
All right, let me erase. Hold on 1 second. Why can't I erase?
This is your last order.
Yeah.
What do you think?
No way. My seniors on I'm not really sure yet.
I think
All right, for
everybody.
some reason it's not letting me erase this, but let's kind of go through these.
Congrats, Jules, that's exciting. It sucks that you have to be online for it. It does suck a lot.
Microphones.
Did you have any like on-campus internships
Okay,
or anything? Yeah, you did.
Yeah, I guess technically I still do.
I'm gonna mute people just for a second. Okay, so going back to this clicker question. If the dot product of two non-zero vectors is 0, the vectors must be perpendicular to each other. The microphones are active after the breakout rooms. Got it. So yeah, if once you leave, please make sure you're muted so that we don't have a bunch of side conversations going on. So first part, if the dot product of two non-zero vectors is 0, the vectors must be perpendicular to each other. So going back to this drawing. So from this definition of the dot product being, come on, A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. You're told that these are non-zero vectors, which means the magnitude of A is not 0, the magnitude of B is not 0. So the only way that the dot product can be 0 is if the cosine of the angle between the two vectors is 0, which means the vectors are perpendicular to each other. So A, this first one, is true. So second part, the value of the dot product of two vectors depends upon the particular coordinate system being used. That is false. It doesn't matter the coordinate system because the length of vector A is always going to be the same. It doesn't matter what coordinate system we're using. The length of vector B is always going to be the same, and the angle between the two vectors has to be the same regardless of the coordinate system used. So the answer to the first one was true. Answer to the second one was false. So the correct answer for clicker question 9.1 is C. Second one. Let me do the mouse again.
Hey, Joe.
Yes.
The breakout rooms, we can just talk about it, but we can't like vote on A or C, right?
Yeah, I was just experimenting with trying to, let me just clear all drawings, see if that would work for doing clicker questions. Is not looking like it's going to work very effectively. So I'll try and figure something else out. Okay, so for B, you're told that the scalar product of A and B is 10, and you're given that vector A has an x component of 3, a y component of 2. So basically, I know that AX times BX plus AY times BY has to equal 10. Now, one thing, the dot product does have units, and it's just going to be the units of A times the units of B. But for this generic example, there are no units. So basically, I need to have 3, which is the x component of A, times the x component of B, plus 2, which is the y component of A times the y component of B, equal 10. And if you look, the only really easy way to do this is just to kind of plow through it. Looking at this, if Bx was 2 and By was 2, then I would basically have 3 times 2, which is 6, plus 2 times 2, which is 4, giving me a total of 10. So the correct answer was E for that particular clicker question. Will we have access to these questions online? Good question. What I'm looking at trying to do is to share I'm using OneNote for this. I'm going to look into how I can share these notebooks with you. So yeah, I'm going to look into that. Okay, let me just pause. Any questions I can answer on these 2 clicker questions?
Hey, Joe, so the scalar product is pretty much just the sum of the magnitudes of the components of 2 vectors.
Say that one more time.
So the scalar product is just the sum of the product of the components of 2 vectors.
Yeah, so there's 2 different ways. Can I move this? 2 different ways. Can I move this too? Sorry, I'm just trying to move stuff on my screen. Oh, okay. So let me go back to lecture notes for a second. Let me get rid of clear all drawings. Okay, so yeah, there's 2 ways that the dot product is defined. Annotate, draw, got that. So 1, it's just the magnitude of one vector times the magnitude of the second vector times the cosine of the angle between it. From that definition, you can show that for two dot products, or for two unit vectors, if those unit vectors are dotted with themselves, so I dot I, j dot j, k dot k, that ends up giving me 1. Just because the length of any unit vector is 1, the angle between a unit vector and itself is just 0. So any unit vector dotted into a different unit vector, I dot j, j dot k, k dot I, those will all give me 0 because the angle between a unit vector and another unit vector is 90 degrees. From that definition, come on. My thing is being weird. Lecture notes. Okay, clear all drawings. From that definition, then you can show a second way of getting the dot product is, clear, redo, undo, clear all drawings, clear all drawings. Okay, I don't know why it's not clearing this, but this is maddening. The second way of getting the dot product is AXBX plus AYBY plus AZBZ. They will both give you the exact same answers.
So we kind of already did that in chapter 4 then, right? When we were just learning about vectors.
I don't remember if I did that. I mentioned that we're going to be looking at multiplying vectors together 2 different ways. First way that we're doing now is the dot product or scalar product. Second way we're going to get to in chapter 12 is called the cross product or the vector product. The end result of that is a vector. Key thing with the scalar product is it's just a number plus units. It's not a vector.
Okay.
Okay. So what I want to do now is just give you a little, let me clear all drawings again, energy overview. So I want to just talk a little bit about energy, give you a little overview, and then probably on Thursday we'll start doing it more mathematically. So just in terms of definitions we're going to care about. Chris, you got a quick question?
Yeah, back to that second question of the
Clicker question?
Yeah, doesn't that one just have an infinite number of answers and not 2 and 2?
Oh, you could, there are different possibilities that you could arrange so that they will give you a vector product of 10. Oh, wait, let me think. Is there an infinite number?
Yeah, because if you, yeah, because it's just a 2-variable equation with,
yeah. So this was just given these 5 possibilities, which of these 5 is going to give me a cross or a scalar product of 10. And in this case, only E would do it. But yeah, you're right. There are multiple possible answers. Okay, so let's go back to this sort of energy overview. So these are the definitions that we're going to be caring about. Energy, work, system, environment, internal forces, and external forces. So 1, energy and work. Oh, this is no longer a recap. Got to get my other hat on. This is the Joe's teaching at home and staying positive hat. So energy and work have kind of weird definitions. They are sort of circular. Energy is in terms of work and so on and so forth. So the definition of energy is kind of a weird definition. It's that property of an object or system that enables it to do work. And work is basically to exert a force over a displacement. So anytime an object has energy, it has the ability to do work. And to do work on an object basically means you're exerting a force on that object or system over a displacement. So if an object has energy, it has the ability to exert a force over a distance on another object. And in a little bit, I'll go through the different forms of energy that we care about. But I want to just go through these definitions. So a system, there's different definitions of the system depending upon science we're looking at, but in physics, the way we define a system is just a defined collection of objects to be studied. And in terms of a defined collection of objects to be studied, guess who gets to define the system? And the answer is you. So a defined collection of objects to be studied, it's defined by you. So you get to define a system however you want. And the reason it becomes important is because of these definitions of internal forces and external forces. So before I get to that, let me just go back to environment. So you get to define your system however you want. But the reason that's important is because the environment is basically everything that is not part of the system. So once you define your system, it could be a book, it could be a couple of particles, it could be the earth and a ball. Everything that's not part of the system is the environment. And the reason that matters is because there's going to be a difference between internal forces and external forces. Internal forces, if you had to take a guess, what would you think internal forces are? And the answer is forces that objects within the system exert on other objects within the system. So let me just type that out. Forces that objects within the system, forces that objects within the system, forces that objects within the system exert on other objects in the system. So once you define your system, any forces that objects in the system exert on other objects in the system are internal forces. On the other hand, external forces are forces that the environment exert on the system. So those are our definitions that we care about. We kind of go through this one more time. So energy. Undo. Why can't I erase this? Eraser. That's really weird. It's not letting me do that. Clear all drawings. Clear. Why wanted it written? Anyway, I don't know why it won't let me erase that. So energy is this concept that something that has energy has the ability to do work, which means it can exert a force on the object over some displacement. Work, oh great, they're doing work outside, sorry about that. Work is to exert a force over a distance. System is a defined collection of objects to be studied, basically defined by you. And the reason that's important is because anything that's not part of the system is part of the environment. And the environment is just everything that's not part of the system. And the reason that's important is because we're going to start differentiating between internal forces, which are forces objects within the system exert on each other, and then external forces are basically forces that the environment exerts on the system. Quick question, can you guys hear me, or is this outside noise too much?
No, you're fine.
Mine okay?
We can't even hear it at all.
Yeah, I don't hear what's going
on. Okay, good. So let me go down here, mouse. Clear all drawings. Can I move this down a bit? Okay, so here is our basic energy model. And it says this: I have a system that I've defined. Inside the system, energy can be transformed from one form to another. So we have different forms of energy we're going to look at. We've got kinetic energy, potential energy, thermal energy, and chemical energy. Within the system, energy can be interchanged from one form to another. So for example, let's just say I have a ball that's dropping. If I define my This is really loud on my end. I don't know that you can hear it, but it's hard for me to talk over this. So if I define my system, let's say as the ball plus the earth, then what ends up happening is as this ball is falling, it's increasing in speed, which means its kinetic energy is getting bigger. But it's decreasing in elevation, it's getting closer to the earth, so the gravitational potential energy is getting smaller. But what we see for this system is that the total sum of the kinetic energy plus the gravitational potential energy is going to be a constant. So within the system, energy can be transformed from one form to another without loss. So the total energy of the system, if there's nothing doing work on it, is going to be constant. Now, how do I add energy to a system or take energy away from a system? And the answer is doing work on it. So what we're going to see is if I do positive work on a system, and again, we haven't gotten to the definition of work yet, it's all conceptual, but if I do positive work on a system, I add energy to the system. And if I do negative work on a system, I remove energy from the system. So if I wanted to add energy to a system, can I do something here? Hey, so I have an easy button. And let's just say I define the easy button as my system. If I do positive work on this, I could increase its elevation, I could increase its kinetic energy, but anytime I'm doing positive work in the system, I'm adding energy to the system. I could also do negative work. Let's just say I had a car that was moving towards me. I could do work to slow it down, removing energy from the system. That work I do would be negative. Wait, let me just check here. Wait, so what would energy from nuclear be counted under? So let me just say these forms of energy I'm going to look at are not the only forms of energy. These are the main ones that we're going to be looking at. We're not going to be dealing with nuclear energy. I just forget what time is, I'm going to go until about noon. So let me just be specific about some of the types of energy we have. So the forms of energy we're going to be looking at, the main ones, kinetic energy, gravitational potential energy, elastic or spring potential energy, thermal energy, and chemical energy. These are the main forms. Quick little question. If an object in the system exerts a force on an object outside the system, is that internal or external? So if you are exerting a force on an object that's not within the system, that would be an external force that the system is exerting on the environment. So internal forces, again, any forces that objects within the system are exerting on other objects within the system. External forces are forces that the environment exerts on the system. But we could also have the system exerting forces on the environment, but we're generally not looking at that. So let me just talk about the specific forms of energy, and then I want to just preview the equations that we're using for it. So any moving object has energy. We call that energy kinetic energy, and it's the energy of motion. And the equation for kinetic energy that we'll get to is kinetic energy is 1/2 the mass of the object times the speed of the object squared. One important thing, all forms of energy are scalars, which means there is no direction associated with it. And all forms of energy we're going to see are going to be measured in joules. It's just a number. It can be positive or negative for certain kinds of energy, but there is no direction. Why is that the equation? I will derive the equation for kinetic energy on Thursday's lecture, but it just comes out of Newton's second law. Sum of the forces equals ma. Gravitational potential energy. Let's see if I can type this out. This is basically energy an object has, energy an object has in an elevated position. So anytime I have an object that's at some certain height, that object has energy associated with it, because if I drop the object, it has the ability to exert a force on another object over a distance doing work on it. So an object in an elevated position has potential energy. I think of it as stored energy. In general, potential energy usually gets converted into another form, often kinetic energy. The equation for gravitational potential energy is mg times y. M is the mass of the object in kilograms. G is the acceleration due to gravity. Y is just the elevation in meters, how high you are above the reference point. And one important thing that we will go through is you can define y equals 0 anywhere. It's basically like you defining the origin. I can define my 0 height to be anywhere. We'll go through that later. Elastic or spring potential energy. This is energy stored in a stretched or compressed spring. If I have a spring or a rubber band or something like that and I stretch it, there's a certain amount of energy associated in that elastic being stretched or compressed. The equation for elastic potential energy, we're going to use, we use SP for spring, and it equals 1/2 K x squared. Again, I'm just previewing these equations. We'll go through them and I'll derive them. But K is just a number called the spring constant, and it just describes how stiff the spring is. A stiffer spring would have a bigger spring constant, and X is how much the spring is stretched or compressed. Your book uses delta X. I'm just going to use X. The delta X just becomes cumbersome once you start using it in equations. Thermal energy, in a sense, this is really just heat. It's and really sum of kinetic and potential energy of all the atoms and molecules in an object or system. So I really just think of thermal energy as heat. The hotter an object is, the more thermal energy it has. And thermal energy is created anytime friction is present. It is also in the book and describes it pretty well. Yeah, so the equation, just so you know, I'll do some derivations quickly, but the derivation for kinetic energy I will go through because it has some interesting math, but I may not do every derivation just because I want to focus on what's going to help you learn the fastest. And derivations are something that you could look up in a book. So thermal energy. Anytime there's friction present, friction will convert some kinetic energy into thermal energy, and the object will heat up. So we'll get to this, but how much the thermal energy of a system changes is going to be equal to the force of kinetic friction times the displacement over which friction is acting. And again, I'm going to get to that later. These are just previews. And then finally, chemical energy. This is basically energy stored in the bonds between atoms and molecules. So chemical energy is basically the energy I think of being stored in food or gasoline. We'll talk about this more later, but calories is just a measurement of how much chemical potential energy is stored in food, and there's a conversion between calories and joules, and we'll talk about that later. But anytime the bonds of an atom or molecule are getting rearranged, you can have energy being released in the process. So gasoline has a certain amount of chemical potential energy stored in it. Food has a certain amount of chemical potential energy stored in it also. Why does thermal energy include potential energies of atoms? Good question. You're going to study this in detail in Physics 4C, but when we think of thermal energy, it has to do with the chemical energy, well, not the chemical, has to do with the potential energy and the kinetic energy of atoms and molecules. So you probably know that when you heat up, let's say, water, the kinetic energy of the atoms and molecules starts increasing. Well, you also have to look at the chemical energy stored in the, it is a more in-depth question than I can answer just quickly, but you do have to take into account not just the kinetic energy of atoms and molecules, but also the potential energy, because that's part of thermal energy. Okay, let me pause. Let me stop this share for 1 second.
Oh, Joe.
Yes.
So on the note that you had sent out from last year, the thermal energy is negative FK delta R.
So that's good. Let me
That's
share that screen again to go back to this. Under the lecture notes, let me scroll down. Okay, so right here, thank you for pointing that out. Draw. This was a mistake. So this minus sign should not be here. It should just be the change in thermal energy is the force of kinetic friction times the displacement over which kinetic friction is acting.
Okay, thank you.
Okay, so I don't know that I want to go into the math right now. I want to just sort of do that on Thursday. So let me do a quick little recap and then see if there's any questions. So let's move this mouse. Go to energy overview. So again, our basic energy overview is this. We have a system. A system is a defined collection of objects defined by you. Anything that's not the system is the environment. So the environment is everything other than what you've defined the system to be. If I want to add or remove energy to a system, I do that by doing work on the system, which means exerting a force over displacement. On Thursday, I'll get to the actual definition of work. If I do positive work on a system, that means I have added energy to the system. The total energy of the system has increased. If I do negative work on a system, then I've removed energy from the system. The total energy of the system has decreased. Now, what is energy? Energy is just this property of an object that enables it to do work, which means it enables it to exert a force over a distance. And then again, system is a defined collection of objects defined by you. Anything that's not the system is the environment. And the reason we care about it is because we're going to start differentiating between internal forces and external forces. Internal forces are forces that objects within the system exert on each other. External forces are forces that the environment exerts on the system. And then last but not least, we're looking at types of energy. So there's only 5 types of energy we're going to be dealing with in this chapter. We're not dealing with nuclear energy. We're not dealing with solar energy. We're not dealing with other forms that do exist. We're focusing on kinetic energy, gravitational potential energy, elastic or spring potential energy, thermal energy, and chemical energy. Kinetic energy is energy of motion. Any moving object has kinetic energy. That energy depends upon the mass of the object and the speed of the object. The equation, 1/2 mv squared. Again, I'll derive that for you on Thursday. Gravitational potential energy. Any object that's in an elevated position has stored energy that we call gravitational potential energy. Equation for that is mgy, where m is the mass in kilograms, g is acceleration due to gravity, y is the elevation in meters, the height in meters. We also have elastic or spring potential energy. If I have a spring which is stretched or compressed, there's energy associated with that. It's stored energy. We call it elastic potential energy or spring potential energy. The equation is 1/2 k times delta x squared. I'm using x, so 1/2 k x squared. X is how much the spring is stretched or compressed. We've got thermal energy, which is basically heat. As an object heats up, the amount of thermal energy increases, and as always friction, which is causing thermal energy to be generated. In essence, friction will take kinetic energy and convert it into thermal energy. And then last but not least, chemical energy is just energy stored in the bonds between atoms and molecules. When those bonds get broken or rearranged, energy can be released. This is how we get energy from food, energy from gasoline. Whew. Okay, let me stop this share. And I'm gonna take just questions for a minute or two, and then I'm gonna stop this Zoom session. So this is just sort of the lecture material, and then restart the Zoom again as office hours. So any quick questions just on stuff that I've covered so far? Okay, if not, then like I said, I'm gonna, oh, Laura, you got a question? No. Okay, so I'm going to end this meeting for all. I'm going to start it up again in about 3 or 4 minutes. I'm going to have office hours for a half hour where I'll answer questions about anything.
Can I ask just a question about anything really fast?
Yes, go for it.
I just thought, I was curious about, so all of our lectures are going to be around 45 minutes long, but we won't be doing the quizzes on Thursday anymore. That lecture time will just be straight lecture.
Correct.
Okay.
So the quizzes will be, I have them scheduled. That's the last time. And I'm just, I'm keeping these lectures to 45 minutes just because I think sitting in front of a computer for an hour and 20 minutes, it's just too much. And I'm also expecting that people are going to need to be doing more stuff on their own, watching some videos on the Expert TA series or looking over my lecture notes or things like that. Also, every once in a while, I will just create a video that's not through Zoom, kind of like I did before, where I will maybe do some example problems or go through stuff in more detail. So we're not going to lose time in terms of lecture. We have Thursdays when I usually would have a quiz. That'll now be done online. And then once or twice a month or maybe more, I will create a video that I will upload that'll sort of be additional. Soraya.
So what's it called? Oh my God, my brain. So instead of lab, are we going to have a lecture or are we going to watch the YouTube video that you put for the lab?
So good question. So labs are interesting because we still have to have labs. And so nobody's allowed on campus anymore anyway. So I went to campus over the weekend and I got a bunch of equipment, and John and I are basically going to be doing labs from my house. We're going to film the labs, and then you're basically going to take data by watching the movies, watching the videos. And just so you know, I'm going to keep the lab videos. Like if you looked, I did a quick little 10-minute introduction video for lab 7, and then the setup and data taking was another 10-minute video. So, you got 20 minutes of video to watch. I'll be specific for each lab about what you're turning in, but just so you know, there won't be any more formal lab reports. We're just going to make everything informal, and I'm going to keep it short and sweet. So for this particular lab 7, you're really just doing what's on the lab write-up. You're drawing free body diagrams. I really just want to see all of your work presented in a nice, easy way for me to follow. So yeah, so labs, you don't have to go at the exact lab time of 8 a.m. or 11:15 or 2:45. The labs will hopefully be posted a couple days beforehand if I can, but then at any point on tomorrow, just I would say watch the lab, and you should be able to do the lab, do the write-up, upload it, everything like that within 3 hours. And so I'm hoping that, yeah, the labs will be relatively straightforward, but yeah, you're basically just watching the videos. It's not ideal, but.
Yeah, thank you.
Yep. Okay, I'm going to stop this Zoom session for now. I'm going to restart it in about 3 or 4 minutes, and I'll just have a half hour of office hours where I'll answer any questions. And again, if there's some questions dealing with content, I will post a YouTube video of the Zoom office hours. So I'm going to end this, and then if anybody wants to come to office hours, I'll restart this meeting in about 3 or 4 minutes. So see you. Thank you all. I appreciate you guys continuing to tune in at the regular time for lectures. And yeah, I'll see some of you in office hours in a minute or two.